Perfect. All right. So welcome everyone, whether you're online live or whether you're listening to this on YouTube. So today we're going to discuss reinforcement learning as part of the Virtual Summer School in Machine Learning and Electron Microscopy. So initially you might think, what does reinforcement learning have to do with electron microscopy in any way? And so I'm going to convince you that it's actually quite useful for microscopy in many different ways. And so we'll walk through some of the basics of reinforcement learning as well as some of the applications. I'm going to focus the last part on the scanning probe microscopy. However, this is also equally applicable to electron microscopy, and it's in fact work that is currently being done as a collaboration between UTK, ORNL, and other partners. With that said, my name is Rama Vasudevan. I'm from the Center for Nanophase Material Sciences at Oak Ridge National Laboratory. And so welcome to this lecture number 22 in the series. All right, so many of you have probably heard about reinforcement learning, at least if not in terms of what it actually is, at least in terms of computer science news. And so you may have heard some of stories, some things like superhuman performance in games like chess, shogi, Go, and so forth. And so these have made a lot of waves in the last, I would say, 7-8 years. And so a lot of it was driven by research out of Google and DeepMind. And basically the idea here is that they could train a reinforcement learning agent more or less by self-play. So you don't really have to do much to the agent itself. You just have to allow the agent to operate in an environment and continue to play either itself or the other even human opponents. And the agent will learn over time how to make decisions in the environment that can maximize its rewards. And so there have been a lot of studies as to how these kinds of reinforcement learning agents can be made to learn more efficiently and learn better than what humans can actually do, at least in certain closed kinds of environments, such as provided by typical board games. Similarly, you can see sort of superhuman gameplay in things like Atari games. So this is some pioneering work by Mina and co-workers that was published in Nature in 2015. And so they introduced deep Q-learning, which is effectively a Q-learning algorithm using deep neural networks for functional approximation. There's nothing in particular special about the algorithm. The main advance here was that by leveraging the capabilities of deep neural networks for functional approximation, they were able to really scale up deep reinforcement learning such that it became competitive in many of these games where previously, even though the algorithm had been around for 30+ years, it was never really feasible to be able to apply those algorithms to games as complicated as those that humans typically play. But the important thing to note here is that this is not just all fun and games, right? It's not all just RL just because we want to beat humans at different types of gameplays. The real advantage of RL is that it can be applied to a wide variety of environments as long as you can structure the environment in such a way that it is outputting states and rewards to agents from which the agents can actually learn. And it turns out that, in microscopy, this is actually a perfect setting because you can treat microscopy as a similar kind of environment, right? You have a microscope. This can be as an electron microscope, it can be a scanning probe microscope, it can be any kind of microscope really, but it is generating streams of data. So these are sort of the states of the system that you are able to image. And you can actually perform modifications, right? So you can do many different things. You can change imaging parameters. You can manipulate things like dopants on the surface, either for things like doing thermal anneals that are available, laser annealing, for example, that are available in some microscopes. You can change the temperature. You can also use electron beam to position dopants in these systems sometimes. And the key is that by applying these so-called actions or manipulations to the sample, you can image the previous and next state. In other words, you can image what happens after you apply that action. And so this state, action, state, or next state tuple, as it were, becomes a so-called reinforcement learning transition, right? It's a transition between one state to another, which is conditioned on the action that you took to get from that first state to the next state. And so if you talk about this in reinforcement learning parlance, what that really means is that we have from our microscope, we get some state knowledge. In other words, what is the state of our particular system? And sometimes we can also leverage simulations to be able to help us to decode what that actual state is. And based on what we would like to do to the system, we can then train reinforcement learning agents to provide that feedback control. In other words, to determine what actions to take such that we reach our desired state in the future. Of course, this actually requires a significant amount of computational power often, because reinforcement learning, as we will get to, is quite sample inefficient right now. And it may also require some amount of simulations as well, in which case you really need access to cloud computing or HPC resources, depending on the types of simulations that you need for your particular problem. But I just want you to get from this slide that really a lot of what we are doing, particularly when we are trying to manipulate matter using the microscope, can be deconstructed into a simple reinforcement learning problem. It's simple in a sense that it is easy to formulate. It is difficult, however, in a sense that it is very challenging to solve using most traditional means. And so I'll talk to you about some ways that you can actually go about solving some of these problems today. So let's talk about reinforcement learning and what it actually is and what it actually is similar to based on the lectures that you've already heard thus far. So you've already heard lectures on both supervised and unsupervised machine learning, right? So supervised machine learning is a very simple kind of classification, right? So do I have a cat or a dog? Do I have this kind of dopant atom? Do I have a non-dopant atom in this particular image, right? So that's a classification problem. That's a supervised machine learning problem, and that's the typical kind of problem that you would get started with in machine learning. There's also, of course, unsupervised machine learning. So things like matrix and tensor factorizations are some kind of unsupervised approach. Autoencoders are another example of unsupervised machine learning. In this case, we don't actually have labels for our data. You just have the original data itself, and you're trying to learn some features that are present in the data by typically with autoencoders or principal component or factorization approaches, by typically trying to represent the data as some smaller number of basis vectors, right? Or it can also be obviously nonlinear in the case of variational autoencoders and becomes more complicated. But the basic principle is that you don't have labels in the unsupervised case. But reinforcement learning is actually neither of these, right? It's somewhat in between some of both of these cases. And so reinforcement learning deals with a situation where you have agents that operate on an environment. In other words, they perform actions in an environment based on partial information about this environment. Typically, it's partial information. And the environment spits out states as well as rewards. And so these rewards can be sparse. The environment doesn't have to spit out a reward at every step of the procedure. It can maybe only provide a reward right at the end. For example, if you're playing a game, you either get +1 if you win or you get -1 if you lose. But you need to take a lot of actions before you get to either a losing state or a winning state, right? So the rewards can be extremely sparse. It doesn't have to be a continuous function at all. And the environment spits out these states. Often we need to be able to interpret these states. Or in other words, the agent needs to be able to interpret these states so that the agent determines what kind of actions to take. Now, the goal in reinforcement learning is to learn a policy. So what does that mean? So that means that the policy is what determines what kind of actions the agent will take given a particular state, right? So if we learn a policy, the goal in reinforcement learning is to maximize the rewards that this policy can actually accumulate over time, right? So the agent is given rewards, and over time, we want to maximize how much of the rewards the agent actually receives, and so we learn policies that maximize these actual rewards that we end up getting, right? Now, there's a couple of different kinds of policies. So we can learn sort of either deterministic policies or stochastic policies. So I'm not going to talk about deterministic policies so much in this lecture. I'm going to talk about stochastic policies. But basically, a deterministic policy is when given a particular state action pair, given a particular state, the action is more or less deterministic, right? So it's always going to take a particular action. However, stochastic policies are ones where you actually have to sample from a distribution to obtain the action. So if the agent is given a particular state, then there's a probability of taking different kinds of actions. And so we sample from that distribution to get the action that the agent is going to take. Now, you might wonder, why do we do this? Why do we need deterministic policies in some cases and stochastic policies in other cases? A simple example is, let's say that that you have a deterministic policy in a random game like rock, paper, scissors, right? So if you have rock, paper, scissors, and you play it with, with a agent that has a random policy, right? It's only randomly selecting. You can't actually beat a random policy, right? In this case, if you always have a deterministic policy that, if I'm always going to play rock, paper, scissors in that particular order in the game, then you're never going to be able to maximize your rewards, right? The maximum reward you can possibly obtain over time is through a stochastic policy where your actions are actually random. And so this is a particularly very simple example where, because of the stochastic nature of the environment itself, you actually need a stochastic policy to obtain the highest possible rewards in this environment. And so today I'm going to mainly focus on those stochastic policies rather than deterministic policies, although I will touch on that in one of our examples. We can deal with sort of continuous and discrete action spaces. So for example, in sort of games, often you only have sort of a discrete action space, like in the old Atari kind of games where you can move left, right, up, or down. And so this is a discrete action. However, there's also continuous actions, right? So depending on, for example, what velocity you want to go if you're driving a car, that's a continuous action. And we can deal with both of those. And we can even deal with combined discrete and continuous action spaces in reinforcement learning. And as I mentioned before, policies are generated that aim to maximize the expected future rewards that are emitted from the environment. Okay. So how can we think about reinforcement learning? How would you go about learning a particular policy, right? So in reinforcement learning, I mentioned that we don't have labels, right? So this is not supervised learning, so we don't actually have labels. But what are we trying to do in supervised machine learning? In supervised machine learning, what we are trying to do is maximize this particular expression here, right? So what is this expression? This expression is saying that we want to maximize the log probability of the label y given the data x, right? So I have some X's, some inputs, and I have some outputs, which are some Y labels, right? So I have some images of cats, and then I want to say that the label is going to be cats. I have some images of dogs, and these labels are going to be dogs. So what that means is that when I pass an image of a new cat or a dog, then the log probability of that classification has to be increased, right? So that's what I'm trying to do in supervised machine learning, right? But in the case of reinforcement learning, we don't have these Ys. We have these X's, which are our states, but we don't have the Ys. So how do we get those Ys? There's a very simple way to think about this. Let's say that you're playing the game of Pong, right? And so on the left-hand side, you have a paddle. On the right-hand side, you have some kind of another paddle, which is maybe played by another player. And let's say that we are this player here on the left-hand side, right? So we have to decide based on what's happening here, what to do with our paddle. Do we have to move it up or down, right? And so what we can do is we can initially just start randomly applying some actions and seeing what happens, right? So we can do up, down, up, down, up, up. And maybe when we did this particular sequence based on the kinds of states and that we are receiving, maybe we lost the game here. Maybe the ball went past our paddle, and so therefore we say this is bad. In another way, in another game, we again repeat this process. And so this sequence of actions turns out to be good for us, right? So we say these are good. So in reinforcement learning, what we are really trying to do is taking all of these rewards that we get, in other words, the ones which say that they're bad and ones which say they're good, and treating them as labels, right? So we can basically state that we want to be able to maximize, right, the log probability, right, that we take good actions, and then we want to minimize the log probability that we take bad actions, right? So that's basically what we are doing. So we are treating trajectories where we get rewards as our labels through which we can do this maximization of the log probability of taking these actions, right? So that's how you can think about reinforcement learning. Now, reinforcement learning is typically expressed in terms of solving a so-called Markov decision process. And so I'm going to walk you through some of these slides. It's going to take a little bit of time. I do also recommend that you take out a pen and paper for the next part, because there will be some math and there will be some derivations here. So if you have access to a pen and paper right now, I would recommend that you go and get them so that you can study along for the next few slides. But firstly, many of you have probably heard about Markov processes, and a Markov decision process is kind of an extension to a Markov process, where you actually have to take decisions on each state. So these are these circles here in the Markov decision process represent states. The red words are actions, or any of the red letters are actions, and then there's a reward that's given after each particular state. So these actually come from David Silver's RO lecture notes, and if you want to learn more about reinforcement learning, I suggest that you actually study David Silver's lectures. This is how I learned it, and it's actually a very nice course that he has for free that you can look online, okay? This is from University College London, I believe. So let's say that many of you are students here, right? And so let's say that you initially are in a particular classroom. Let's say that you're in this particular classroom right now. And so you actually have a choice, right? So what can you do, right? So maybe one thing you can do is you can log on to Facebook and see what your friends are up to. Although these days maybe this should be Instagram or some other social media network. Nonetheless, you can do that. And unfortunately, what that does is that it gives you a -1 reward, right? Because it's not actually particularly good for you. And you transition to a state where you continually try to look at Facebook feeds. And so every time you stay in this state and you take this particular action, you get a -1 reward. You can quit that, right? And so you won't get any reward for doing that, but you can come back to the classroom. But if you choose to decide to study, for instance, right? What happens here, right? So studying is hard. So initially, maybe you get a negative reward, right? Because it's kind of difficult to do. But you can continue to study. And let's say that if you can choose to terminate and you can actually go to sleep. This will be bad because that means that when you terminate in one of these states, in these square states, then your total reward that you got was, in this case, -2 plus 0 is equal to -2. So therefore, your total reward in this Markov decision process by following these actions was just -2. On the other hand, if you continue to study, then you have -2 here, and then you have -2 here. So you have -4. But then because you studied a lot, then you can actually pass the final exam. And so therefore, if you study a bit further, you'll actually have a reward of +10. And so now when you get to the terminal state, you have a final reward of +6, right? When you add up all these rewards together. On the other hand, you can also choose that, you've had enough of studying and you want to go and have a drink. So if you go to the pub and have a drink, then initially that might seem like a good idea because you get an immediate reward. However, with some probability, depending on how much you drink, you can either regress a little bit to 1 class behind, or you can regress even further to 2 classes behind. And so obviously when we go through this particular loop, this is not going to be a favorable outcome for the student. And so you want to avoid trying situations where the agent is repeatedly accumulating negative rewards and never getting any positive rewards, right? So how do we solve this particular Markov decision process? So in this case, it's very straightforward. Like you can actually just have a look at it and do it by eye. But typically these Markov decision processes are much more complicated, and you may even have infinite numbers of states. But the point is that you can visualize these trajectories through this Markov decision process as these tuples, right? You have these state, action, reward tuples. So I'm in a particular state, I take an action, and then I get a reward, and then I go to another state, I take another action, get another reward, and so forth. And I get what's called these trajectories through the Markov decision process, right? And so once we accumulate many of these trajectories together, then we can actually use them to be able to solve this reinforcement learning problem, right? And to solve this Markov decision process. And I'll show you how we actually do that. So here are some definitions. Firstly, I want to apologize for my poor handwriting here. This is kind of difficult to write on my particular laptop, but I hope you can still follow along. So the definition here is that the first thing that you need to know about is stochastic policies. So our policy is going to be represented by this letter pi, and it is going to be parameterized by parameters theta. So usually this is a neural network, right? And so what we do with this neural network is that we effectively input states into this neural network, and out comes some kind of parameterization of the policy. In this case, we're just going to use a Gaussian distribution. And so the Gaussian distribution is defined by the mean of this distribution and the variance of this distribution. So anytime I get a state, I plug it into this neural network, which is my policy, and which is my policy network, which is governed by these parameters theta. And so I can then get these mu and sigma parameters from which I can construct my actual policy that I sample from. And so that's going to be here. And so what happens here is that once I'm given this particular state, I can construct a Gaussian distribution of this particular mean and variance, and I can sample from this distribution to get what action I should be taking in that particular state, right? So you can also notice that these are continuous actions sampled in this way, right? Because this is a continuous distribution, and so therefore I can sample actions and get continuous values for my actions conditioned on the state that I sample from. So that's what this is saying here. This AT, this is action that I'm taking at time step t, is sampled from the policy, and it's conditioned on the state that I'm in that time. Okay. So as I mentioned before, you can take trajectories through the Markov decision process, right? So these can be state, action, reward tuples. So in this case, this is state 0, then I take action 0, maybe there wasn't a reward, then I state 1, I get action 1, and so forth. So sort of sequences of states and actions. And in a stochastic environment, it's governed by environmental dynamics conditioned on the state and action, right? So what does that mean? That means that, let's say that I'm in a particular state, I take a particular action, right? Depending on the environment itself, right? And there is a probability of transitioning to a particular next state, st plus 1. And that's all this is saying here, right? So I take my st plus 1, and it is coming from this environmental dynamics term where, conditioned on the previous state I was in and the action that I took, there's a probability of transitioning to that particular next state that we end up transitioning to, right? So this is very straightforward. All right. Now, there's some definitions here. So the first thing I want to define is the so-called reward function, R, right? So what is my reward function? My reward function is basically stating that if I was in a particular state, I took a particular action, and I ended up in the next state, right? Then I should get some particular reward. And so my reward function is a function of all of these particular variables, right? So typically we don't write st plus 1, we just write it as R. The reward function is a function of the current state and the action pair. But so this is just, for convenience. And the other thing that I want to define is a so-called discounted return, right? So I have these trajectories through my Markov decision process. And so I have I have a reward function which tells me what kind of rewards that I'm going to receive from the environment, right? So this is actually encoded in the environment itself. The environment knows that if you're typically reward functions are given by the human operator in this, in most cases. And so, or designed by the human operator. There are other ways to do that, but I'm not going to touch on that. But let's assume that the reward function is a known function that is at least known by the environment, not by the agent, but it is known by the environment. And so the environment spits out those rewards. So one of the things that we want to talk about is a so-called discounted returns. So what does this mean, right? So if I get, for example, going back to that initial student and the Facebook example, right? You can see that there is a benefit, obviously, to waiting for your rewards, right? Because if you move through particular states, there's a chance that you can actually, by waiting for a particular state to come along, you can actually get significantly more rewards, right? So what does that mean? That means that we want to be able to have some kind of trade-off between immediate rewards as well as future rewards that might appear by following our particular policy. And so our discounted, we have a concept called a discounted return. In general, this is also true in sort of economic speak, the kind of rewards that we get, we prioritize immediate rewards to some extent, but we also do not want to completely discount, future rewards that we might obtain because they could be quite big, right? So the way that we do that is that we define this discounted return, which is R as a function of these trajectories from the time t equals 0 to infinity of gamma to the power of t multiplied by R of t, where this is this function here of the reward function. So, and this gamma is the so-called discount factor between 0 and 1. So what does it mean when it's 0? So when it's 0, that means that, this particular term drops out. And so all you have is this reward function. And what that means is that, of course, you have absolutely no horizon, right? So when you have no horizon, that means that you basically are only prioritizing the immediate reward. On the other hand, when you have 1, which is an infinite horizon, that means that your gamma is such that you want to be able to look really far into the future, right? So this is sort of how much time in the future you want the agent to pay attention to for accumulating rewards through this process. And so you typically have values of gamma between about 0.9 and 0.99 for most scenarios, because you try to make sure that there is some kind of long-term horizon for the agent to be able to learn from rewards. If the agent only learns from immediate rewards, that might not always be the best strategy, and it might be better in case there are higher rewards in the future to be able to have a larger kind of horizon to look at. Okay, so the RL problem itself is very straightforward, to be honest. It is, how do we adjust the policy parameters theta, right? So we have this policy that is governed by these neural network parameters theta, typically neural network parameters theta, and we want to maximize the expected returns, right? So let's write an objective function in this way. So our objective function, we're going to call it J, is a function, right, of this policy that we are having, is equal to the expectation of the rewards that I get for trajectories tau, where the trajectories tau are sampled from my policy itself, right? So we can sample from the policy. In other words, we can get actions from the policy. We can then apply those actions to the environment, and therefore we can get these trajectories tau, right? So what is the expected rewards, right, or the returns of those trajectories, right? So I have some amount of trajectories that I gather, and I have some amount of rewards that were obtained from those trajectories. We want to maximize this objective function J, right? In other words, we want to maximize the expectation of these rewards by adjusting the parameters of the policy theta such that we can maximize this J value, right? So we can maximize this objective function. So some definitions here, which you probably already know. If you don't know, it's relatively straightforward. What is this expectation here, this funny E? Well, this funny E is actually just defined as the integral of the expectation of the variable x is just the integral of x times f of x dx, integrated through the domain. And so in the discrete case, it is just sort of the weighted average, right? In other words, this is, you can think of it as, what is the expected value if I keep drawing from x if I keep drawing x, what is the expected value in the infinite case, right? If I keep drawing infinitely many times, they should converge onto some particular value, right? And so this expectation of this random variable x is given in the continuous case by this expression, and in the discrete case by this expression. And so we want to use gradient ascent, right, to find out how to move the policy parameters theta in such a way so that we can maximize this right-hand side of this expression, right? So in other words, we want to find out how to move theta in the k+1th step to be equal to the theta at the kth step plus the gradient of this objective function, right? So this is sort of very straightforward, sort of high school or first year level undergrad math. And so now let's expand this out a little bit, right? So right now what we have here is we want to find the gradient of this objective function J, right? So with respect to theta. So when we do this, okay, we can just write this gradient of this objective function here. So we can do gradient with respect to the policy parameters theta of this expectation. And then we can just expand the expectation, right? So this is very straightforward. As I mentioned before, the expectation is just the probability, right, of finding these trajectories tau, right? So if we have rewards as a function of returns as a function of these trajectories tau, then I have a probability of obtaining these trajectories tau conditioned on the policy parameters themselves, right? Because depending on what my policy parameters are, that's going to determine what my trajectories through the system are. And so I have this particular expression here, and then I just again multiply by this r of tau again, because this is the definition of the expectation itself. Okay, now I can move the gradient inside, and then I can do something called the log derivative trick, right? So by moving the expression this gradient inside this integral, we can perform this log derivative trick where we can rewrite this expression as this expression down here. And so where does this come from? This is something that you probably remember from high school or from first year math, which is a very simple trick where if you are taking the derivative of the log of a function with respect to x, in this case f of x, then that is equal to f dash x on f of x. And so if you rearrange this, what that tells you is that the derivative of a function is equal to the function multiplied by the derivative of the log of the function, right? So that's basically what we are doing here. So if we follow that through, and so these are actually all in your lecture notes as well that you can get from GitHub. You can rewrite this as this expression as this expression below. Again, this is sort of f of x times the log of the function with respect to times the derivative of the log of the function, sorry. And then if you actually look carefully, you can actually rewrite this as an expectation, right? So this actually, if it follows on again from the definitions of what the expectation actually is. And so you can rewrite this in this particular way. And so what we do then is that, okay, so how do we calculate what this actually is here, right? So we have this term, the gradient with respect to the policy parameters theta of log of the probability of the trajectories conditioned on theta multiplied by the returns as a function of the trajectory. So this is kind of very interesting to look at, but how do we actually compute what this actually is? And so it turns out that it's actually relatively straightforward. So if we want to find what this term actually is, right? What is the log probability that I take a trajectory tau conditioned on these, what is this expression on these policy parameters? It's actually quite straightforward. The probability of a given trajectory is simply the probability that I took an action at a particular state, and then I took the next action at the next particular state, and then I took that next action. And so I just multiply all of these probabilities together, right? And so where do those probabilities come from? They come from the policy itself, right? Because the probability is coming from the policy itself, which is telling me what is the probability that I'm taking a particular action given a particular state, right? So there's no real environmental dependence, right, on the values of theta here, right? So the environment doesn't come into the picture here in terms of the dependence on these theta values. And so we can just multiply these probabilities together if we just take the policy itself. However, it's easier or numerically easier instead to take the log probabilities, because then we can just sum them instead of having to multiply them, right? So we take the log probability here, and so what that ends up being here is that we can rewrite this expression as this sum from t equals 0 to some particular time step t of the gradient with respect to theta of log of the policy log of pi with respect to log of the policy, sorry, with the again with the actions conditioned on the particular states multiplied by the returns that I get by following these trajectories. So how do we do this, right? So we have this expectation here. So how do we actually estimate the value of what's inside here? And so we can do this numerically, right? So we can get a bunch of different trajectories, right? Let's say that we have a bunch of different trajectories D, and so these are trajectories from I equals 1 to n. So we can just estimate what this actually is by sort of taking the mean of this particular expression, right? So I take these trajectories, I calculate what this actually is, and I just take the mean, and that's going to give me my expectation, right? So going back to, if you write this down, what it actually looks like, the gradient of the objective function with respect to the policy parameters is this expectation here, which we just mentioned. And so what does it actually mean, right? So what it means here is that we want to move the policy parameters theta in the direction of increasing returns, right? This return function g of t, which is what I mentioned before in the last slide as r. So what this suggests here is that if we have parameters of our policy which are good, then these returns, this gt or r of tau value would be good, right? So we want to move the policy parameters in the direction where these returns become good and discourage movement in directions where these values become bad, right? So that's all this is saying. Can we maximize the probability that we're going to take actions that are going to maximize these returns, right? That's all we are saying here. And so we want to move it in the direction, or we want to move the objective function j in the direction, we want to move the policy parameters theta in the direction where this j value can become maximized, right? So I hope you got that. Again, you can follow along in the lecture notes that are on GitHub if you want to go over that again. But it's actually a little bit more complicated than that in a real scenario. And the reason for that is because if you actually try to compute this in anything but the most trivial problems, you'll find that there is a very high variance to this particular expression here because g of t has very high variance, right? So the returns themselves often have very high variance. Why is that? Well, let's say that you're in a particular game, right? And so sometimes you will get 50 points at the end of the game. Sometimes you'll get 100. Sometimes you might get 5,000, and many times you'll get 0, right? So the variance that you're getting by in this particular process is extremely large, right? So it becomes if the variance is very large, then estimating this expectation becomes very much challenging and pretty much very difficult to do unless you have a huge number of trajectories, right? Because the dimensionality of the system is so large, unless you have typically millions of trajectories, estimating this expectation becomes a huge challenge. And so there have been ways to try to reduce this particular variance. So what is one way to reduce the variance? Well, one way we can do it is by we can define a so-called advantage function, right? So rather than just multiplying by the returns themselves, what we can do is we can say that we want to find out how good our actions are based on some kind of advantage function. And the advantage function is basically equal to the so-called action value function, or Q function, minus the value function. So in more sort of simple parlance, what this is saying here is that rather than just multiplying by these returns, we want to have a baseline, right? We want to have a baseline that we want to figure out is a pretty good baseline. And if we are doing better than that baseline, then we should be encouraging those actions. And if we're not better than than that baseline, then we should not be. And so by subtracting this baseline, we can actually greatly reduce the variance of these returns. And the way that we do that is by effectively finding the value of the state that we are in. And so the value of the state is, again, this is typically done by a neural network. And so there's a neural network which is acting as this baseline value, and it's trying to estimate the value of being in particular states. And so we'll talk about that a little bit later, particularly when we get into the Colab notebook. But suffice to say that there is a way that we can calculate what this value of the state is based on these trajectories. At least we can estimate it. And so we can use that by plugging this in to this formula. And so we can, instead of multiplying by this G of t value, we can multiply by this advantage function here, as long as we can estimate what this advantage function actually is. And so this is called the so-called actor-critic method, where the actor is the policy, the actions that are being taken, and then the critic is the so-called estimate of this value function, right? The baseline that we subtract from. And so the actor is really trying to perform an action, and the critic is telling the actor how good that action actually should be based on the inferences of what the value of the state actually is. And so here, the end state is that we really encourage actions that increase the so-called advantage, right? This advantage function. All right, so with that said, I'm going to talk about 3 different examples of reinforcement learning as they're applied. And so one of them is going to be a case of sort of, these are all just simulated examples before I'll get to an experimental example. But on the left-hand side, we have one of synthesis of a particular material system. In the middle, we have an example of, again, manipulation of dopants through in a molecular dynamics simulation, but this is also actually doable through the scanning transmission electron microscope. And on the right-hand side, we have another example. This is actually published, by the way, in 2022 in MLST journal about moving defects in ferroelectrics. Okay, but these are all simulated. So I'll just briefly walk you through this before we move through to the experimental part. So the first example is, let's say that we're trying to deposit a film, right? And the film might be grown by post-laser deposition. It might be grown by molecular beam epitaxy. But we have a simulator in this case, or we have an environment. And so this can either be the real system. In this case, it's just a kinetic Monte Carlo simulation that I wrote with some collaborators, Lucas Wilczek being the main person who helped with the simulation. But we basically wrote this simulator for 2 different kinds of atomic species. And so they sort of grow as we add more atoms to the system. And so you can see how that happens, that as we grow the system, you can actually have a look at the surface projection, how the surface looks over time. And we can calculate the roughness of the surface, right? So that's something that's here, and we can have a reward signal based on what this roughness value actually is. And there are 3 different actions that we can take at any time step. We can change the temperature of the system. We can change the deposition rate of atom species A, the red atoms, and then we can change the deposition rate of the species of atom B, right? So these are the actions that one can take. And what we are trying to do is trying to minimize or keep the surface roughness to within a particular target value. And so if we use this actor-critic algorithm, we find that, and we train the system to be able to try to minimize or keep the roughness within this blue line here, or within a good distribution of this blue line. You can see that, over time, although we start with many different realizations, right? In other words, we have different roughnesses to begin with. They all sort of end up pretty close to this final target value. Whereas if you compare that to taking random actions, you see that there's a very large spread, right? So clearly the agent is learning how to manipulate the temperatures and deposition rates to keep our roughness to particular values, right? So this is kind of a very interesting test use case, although of course it is still in simulations land, but it shows that there is a potential here for using reinforcement learning in things like pulse laser deposition or molecular beam epitaxy. The next example I'm going to talk about here is anatomic manipulation. And so again, one of the things that you need to understand about reinforcement learning is that every example that I'm going to show is going to have an environment which has states and actions and then rewards, right? So in the previous case, our rewards were what was the surface roughness, and then the states were the surface projections. In other words, how the surface looks like over time. And so if you can formulate your problem in terms of a reinforcement learning environment, then you can probably use reinforcement learning to solve that particular problem, given enough time and compute resources, really. So that's really what it requires. But let's do that for this particular case of moving silicon dopants in graphene through molecular dynamic simulations. So this is actually a problem that can actually be done on the STEM, and there's been a lot of work out of Oak Ridge as well as other places where they have been able to move silicon dopants using electron beam in graphene. And so we wanted to see if reinforcement learning, at least in principle, could be utilized for this particular process by trialing it in a molecular dynamics environment. And so we created, with the help of Ayana Ghosh, who has been, who probably you've heard of before in these lectures. She helped with performing these simulations, where what we do is we place dopants in different positions, and then we can modify the momentum of these dopants by sort of simulating as if there was an electron beam that was imparting momentum changes to these particular dopant atoms, right? And so it's a very nonlinear problem. So if you change, for example, the dopant position, the momentum that is imparted on the dopant in the X and Y directions, you can see that, it's a very nonlinear problem in terms of how the system actually responds to these changes in momentum. And so what we wanted to do is to try to find out how can we move dopants together, for example, towards the center of the lattice and form clusters of dopant atoms and different kinds of structures. So the way that we do this is that we construct a policy. And so our policy is, as I mentioned before, it's just a Gaussian distribution. However, in this case, it's a multivariate Gaussian problem, because we actually have 3 different dopants that we are trying to move. And so we want to be able to impart momentum transfers to all 3 dopants, right? So dopant 1, 2, and 3. And in order to do this, that means that we need a 3-dimensional multivariate Gaussian policy. And so basically, we have to output 9 different means and variances, right? When we actually look at our actor-critic network. Anyway, we can do this. We can train our policy, and so we can apply some different kinds of regularizations. I won't go into it. You can read about it in our paper here. But basically, you can play this. Here we go. You can see that after the agents are trained, then what happens is that eventually these dopants start to meet somewhere towards the middle. It's not perfect because it's a very stochastic environment, as you would expect. However, you do start to see that the agent is learning how to manipulate the dopants to achieve at least close to the rewards that we want. Okay. And the interesting thing about this is that when we actually train reinforcement learning agents, that in order to be able to have control over the dynamics of some kind of environment, you actually have to learn something about the dynamics of the environment, right? So the dynamics are inherently encoded within the policies, and we can inspect the policies to get some better understanding about the dynamics of our environment itself, which can be quite challenging through traditional means. So what do I mean by that? So let's say that I have a particular state. In this case, it's sort of the positions of the atoms in the system, and so I then pass my state through my actor-critic network, and then I look at the multivariate Gaussians that are actually coming from this, right, in X, Y, and Z for the 3 different dopants. So one of the things that happens here is that if you look at this Z value here, you would think that in order to move dopants on a 2D surface, you just have to provide momenta in X and Y. You wouldn't have to do it in Z. But it turns out that it's actually a more favorable situation to have a non-zero value for the momenta that's actually transferred to the dopant in the Z plane. And the reason for that is because there's a little bit of torque that happens, and so by applying some torque to the dopant and pushing it out of the plane, the energy barrier to crossing to the next lattice site is actually lower. And so this is actually shown by first principle simulations as well. But this actually comes naturally out of our policy itself. And the reason for that is because the policy is trained with a regularization to try to reduce the amount of momentum that's actually transferred to the dopants themselves. And so it tries to find lower energy pathways to do this. And so by inspecting the policies themselves, you can see that in fact we have non-zero values in many cases for the Z momenta that's actually transferred to these dopants, right? So the point here is that policy inspection may become, kind of a useful tool to understanding the dynamics of our system. And we see this over and over again in reinforcement learning. And I think it's something that is quite useful for physics and material science problems, because traditionally reinforcement learning has been used in areas like robotics, healthcare, and so forth, where there isn't really much to be gained by looking at policies. It's more or less used as a control system. But here we can actually understand more about the physics of our system by looking at what's actually being learned by the reinforcement learning agent. Okay, so the final thing that I want to talk about here is manipulating defects in ferroelectric materials. And so this is some work that we did where I actually wrote a simulator that you can actually find the simulator on my GitHub, called FerroSim. And so many of you probably know that we are kind of very interested in ferroelectric materials and have been studying them for many decades. And so I created a very simple sort of 2D discrete Landau model to simulate ferroelectrics. And this is basically like some cross between a traditional thermodynamic Landau model as well as a traditional Ising kind of model, where we consider nearest neighbor interactions. And so the free energy function here is given by this expression, where you have the 2-4 expansion of the polarization, which is the Landau expression, which comes from the Landau expansion. And then we have a electric field term, which is something that we can apply to the system. And then we have nearest neighbor interactions and this coupling constant K. And so we can then analytically derive the gradient for this. And so we can look at the dynamics of our system as we change things like values of K and as we change things like values of the electric field in this particular case. So we can also add defects, and the defects can for example, asymmetrize the potential well, or they can change the barrier, the heights themselves of these switching profiles. And so we can use this particular toy model to be able to see how defects adjust the polarization profiles that we end up getting when we solve these equations. So the challenging part here is that it's a very dynamic system, and so we don't particularly know how we should be placing defects in our system to be able to, for example, maximize some kind of topological feature of our polarization vector field. So let's say, for example, here's our polarization vector field, and we are trying to maximize the curl of this vector field. How do we move the dopants, in particular ways to be able to maximize this, And so the one way that we can do that is we can use reinforcement learning to figure out what is the best strategy to move these particular defects. And so as an input to the reinforcement learning agent, we have the polarization map, and we run it through some convolutional layers. And then we also have sort of a defects table. In other words, the position and location of all these defects that are present. And then we can, from this, output the so-called action value function, or Q value. So remember how I mentioned that there's both deterministic as well as stochastic policies. In this case, we have a deterministic policy. And so what this basically says is, what is the value of taking a particular action given this particular state, And so these Q values are sort of what you can expect to obtain if you took this particular action and you followed the policy through to the end, So we can take this and we can look at the argmax of this Q value. So whatever action has the largest Q value, we just simply take that, and then you can translate what that number is to what kind of action we should be taking. In other words, which dopant we should be moving, so which defect we should be moving in the system, and then run the simulator again. And when we run the simulator again, it then provides us with the next state, and we continue that and for a given number of steps before we say the simulation is over. Okay, so let's start from a random state. So this is the starting configuration, and it's always random. And so this is as like something like, let's say, in some kind of paraelectric state, or just cooling down through the transition temperature as the polarization starts to appear. Initially, it's just going to be more or less random, but we can start to move the defects, right? And as we progress and as we're cooling it down. So what we can do is here, after moving the defects, in this case, we have 3 defects. After the end of the particular simulation, we have a particular reward, and the reward is the curl of this particular polarization vector field. If we look at the trained agent compared to a random agent, you can see that the random agent performs with a very wide distribution of the rewards, whereas the trained agent performs with a very narrow distribution, but it's always above the mean of random actions, right? So this shows you that it's a very challenging problem to actually solve, but reinforcement learning enables you to always, more or less always do better than the mean of taking some, random policy. And in a very stochastic and changing environment, this can actually be very difficult to do. Interestingly, the way that the agent does this is actually to move these defects in what looks like kind of large-scale triangular patterns. And we've saw this over and over again. And I can show you an example of a particular agent run where the simulation is progressing and the agent is moving this particular defect in this particular position. And again, it really does, you can also see the changes in the Q values as we move through different states. And so that tells you what action the agent is going to take. But yeah, we often see these kinds of triangular patterns that are created. And so that gives you some idea about sort of length scales in the system itself. You can also have a look at what happens when you try to provide impossible goals. Things like how do we try to align the polarization against or sort of not in the direction of the applied electric field. And so the way that the agent tries to maximize the reward is to create large regions where there is almost zero polarization, because every time you have zero polarization, that does not contribute so much in terms of a negative reward compared to regions where the polarization is aligned with the electric field. So when you try to maximize this reward, that's sort of accomplished more or less by moving defects such that you have minimal polarization in a large volume fraction of the sample. But again, this is sort of very interesting that you can provide, rewards which are impossible to obtain, but still get some very interesting physics results out from the end of your study. So what about experiment, right? So now we're going to move on to the experimental part. Now, again, we're going to stick to ferroelectrics, but rather than moving defects, what we can really do in ferroelectrics with the scanning probe microscope is we can move domain walls, and we can easily move domain walls by applying different kinds of actions. In other words, different kinds of biases or voltages that we apply to a scanning probe tip while we place the tip on or near a ferroelectric domain wall, right? So let's say that we want to optimize a sequence of bias pulses and create regions of, let's say, high curvature at the ferroelectric domain wall. Well, how would we do this, right? So we have a state. In other words, we have what our image of the current domain wall looks like. And then we have some actions that we can take. We can move the tip to different positions. We can change the voltage that we are applying, and we can change the bias pulse width. In other words, how long we apply the voltage for, and then we can image again. So we have these transitions that we can collect. So the first goal here is that we need to write some kind of automated script to collect data on the state transitions with some kind of, let's say, random policy. Why might we want to do this, by the way? Just, it's not just because we're interested in trying to do reinforcement learning, or that is one of the motivations. It's really because, this goes back to one of our first papers. This is actually my first paper, by the way, on exploring topological defects in ferroelectric bismuth ferrite thin films. But basically, if you apply voltages in these ferroelectric materials in particular ways, you can form very interesting kinds of topological defect structures, and they can have very different properties to the bulk of the domains that surround them. And so it's very interesting to be able to know how to create some of these topological defect states by carefully applying voltages at different parts of the sample. Anyway, what we need to do is we need to be able to collect these transitions. And so we can write these automation scripts and collect transitions. And here is an example of that happening on a lead tight net sample. What you see on the left is the initial state. Then the red dot is actually the tip. And as the tip moves and finds domain walls, it then applies some random actions, in other words, different voltages and different pulse widths. And once it does this, it has the next state on the right-hand side, and you see the difference image on the far right-hand side. So this shows you the amplitude and phase of this data. I'm going to run it again. But every one of these represents a transition that we can use to actually learn from and then train our reinforcement learning agent. But before we get there, here's another example. You can do this in sort of a shotgun mode where rather than just leaving the domain wall to be displaced, we can every now and then reset the domain wall to its original position and get more data this way. But the point is that, it's possible to collect thousands of these kinds of transitions by automating our microscope. All right, so once we have this data, the first thing we need to do is we need to have a reinforcement learning environment, right? So we can actually learn even without an environment using things like offline reinforcement learning, but I'm not going to touch that today. Typically, what you want to do is you want to be able to learn an environment, and you want your reinforcement learning agent to be able to interact with that environment and then learn a particular policy. So let's take the images from our from the last slide. And so we have an initial image. And so from that image, I'm going to identify the domain wall. And so this can be done very easily, either through computer vision approaches or just, in this case, simple thresholding. But we can have a look at the position of the domain wall, and we can have a look at what happened when we applied a particular voltage at a particular location, right? So in this case, here's our state, which is just a 1D vector of this particular length. And we have the next state, which is again a 1D vector after a voltage was applied at this particular position, indicated by this dashed line. And the voltage parameters were, in this case, -9 volts for 283 milliseconds, okay? And so we have this difference, right? That's, in other words, the difference between the state and the next state conditioned on the action that was actually taken. So what we need to do is we need to take these and we need to be able to create an environment where we can predict what's going to happen to the domain wall based on the current given state, what happens when you apply a particular voltage at a particular location, and then the environment should then spit out what that domain wall should now look like based on those particular actions, and it should continue to do so as we add more and more actions. What we found, however, was that even with a few thousand transitions, it's insufficient to be able to give you enough data to train some of these models. And so what we needed to do is we needed to leverage our physics knowledge. Basically, we need to modify the loss function to include some basic elementary physics. Things like if you apply a positive voltage in this case, we should have positive displacement. And if the model predicts something other than a positive displacement, then we should penalize that. Similarly, if I apply, let's say 5 volts and the domain wall moves a little bit, then if I apply 6 volts from the same initial state, it should move a little bit more. It should certainly not move less, right? So there should be a monotonic increase as I increase the voltage in a given state. And so there's a penalty term for deviating from monotonicity. And so these are just added to a loss function of a simple neural net model that we can then create the surrogate model for this reinforcement learning environment. And so we can play with this reinforcement learning environment by, for example, changing the voltage and seeing what happens. So obviously, when you change to positive voltages, you get these positive displacements. And when you go to negative voltages, you get these negative displacements exactly as you would expect. And similarly, as you increase the pulse width, you sort of increase the magnitude of which the domain wall starts to move out. So this is all working as we expect now. Okay, so one of the interesting things is that this is not a simple model which is just telling you domain wall displacements, as a function of actions, right? It's actually telling you it actually has some amount of physics that's encoded into it based on the current existing domain wall profile. So what do I mean by that? Let's say that I start with a flat wall and I'm applying some voltage, right? So I apply some voltage in the positive direction or negative direction, and I can also change the pulse width. So here we're just applying positive voltages, right? So from the flat wall, you can then start to bulge the domain wall out. And so for increasing voltages, you actually get, some increase amounts, it sort of saturates to some extent, but it does actually move out to larger domain wall displacements. So this heat map here is showing you the maximum displacement of the domain wall as a function of these parameters of the voltage and the pulse width, assuming that we started from an ideal flat wall configuration. Now, however, let's say that we started with an initial bulged wall configuration, right? So we have a domain wall where we have a bulge, and then we try to apply more voltage to be able to extend this bulge. Now, unfortunately, this is actually already a very high energy situation, right? So the domain wall does not want to be in a situation where it's already very, elastically strained. And so what happens is that when you try to apply more voltage in the positive direction, it actually doesn't move all that much initially. However, what happens is that if you apply a very small negative pulse, it really does like to flip back to its flat configuration. And so the way that you can see that is that there's some significant amount of difference between these two heat maps. And in fact, there's a significant amount of asymmetry. You can see the left-hand side is much brighter. In other words, the negative voltages induce more displacement than the positive voltages if you're already in a strained case. And this is exactly as we would expect from some phase field modeling, which was done by some collaborators at UC Arlington, Professor Yi Kao from UC Arlington, and his student Bharat Pant did these simulations for us, where they showed exactly that particular scenario, where if you start from a flat wall and you apply some voltage, you can bulge the wall out. But in order to move the wall even further, it's more difficult. But if you want to move it back to its initial flat configuration, it doesn't take much energy at all to be able to do that because it's already in a very high susceptible state. Okay. Again, we can then take this particular surrogate model. We can then create our reinforcement learning environment and train our agent to be able to make different kinds of domain wall modifications on this environment. And so here is an example. Like, let's say that you have 20 steps. In other words, you only have 20 bias pulses you have to play with, right? How would you craft the reward function? In this case, we have a reward function which is crafted as this kind of staircase. So we were trying to get the agent to move the domain wall in such a way that it creates this kind of staircase pattern, right? And so this is the final wall that it ends up coming up with. And you can see that, it's really learning to try and apply more voltages, higher voltage pulses on the left-hand side, and then smaller ones on the right-hand side. And you can visualize that in terms of this particular plot of voltage versus pulse width versus action number here, right? So you see a bunch of ones where it's sort of higher on this side, and then those seem to be corresponding to more on the left-hand X positions. And then the lower ones are more on the right-hand side where you have lower displacements of the wall. It's not perfect. We still need to do more training probably to be able to perfect this. But the interesting thing about why this might be useful is that you can start from any kind of wall configuration, right? So regardless of how your domain wall starts out, if you have a target structure, you can continue to play with it until you reach the desired structure that you actually have. And you can get more control over this than a traditional lithography kind of means, where you just assume that, by applying a certain amount of voltage, you get a certain amount of wall displacement. Because it's a very dynamic process where, for example, over time, there can be changes. There can be changes depending on the tip condition, but also there can be changes depending on the surrounding domain wall structure or the existing domain wall structure itself. And so being able to have an agent to be able to do this in an automated way can really allow us to be able to use reinforcement learning to maximize particular kinds of target properties. Let's say that instead of using the reward function as some kind of structure of the domain wall, we can instead maximize for some property of the domain wall. Let's say that we're trying to find the kinds of wall structures that give us the most elastic softness. We can optimize for that. We can optimize for things like photoconductivity. Maybe that would be enhanced around regions where you have high domain wall curvature and so forth. So it's it's a good method to be able to optimize both for structure as well as properties in an automated way, if you can train reinforcement learning agents to do so with enough data for a surrogate model. All right, so with that said, I want to take any questions you have before we move on to the Colab side. Are there any questions? Okay, so let me stop the sharing and then let's get to the Colab side. Okay, so hold on a second. All right, I guess you can see this screen now.
Yes.
Yes. Okay, so if you go to the ML electron microscopy, you should be able to find here, you can just type, I guess. I think it's here. So if you, I guess, yeah, you can probably see this screen. So if you go here, this is the notebook that we will be working with. And if I try to find this. I think it will also be here. Here. So if we come here and we want to go down to lecture 22, viral domain walls. Let's see if this works. So what we're going to do here is that we're going to play with that reinforcement learning environment that I just mentioned that was trained from experiments. So let's see how that goes. All right, so the first cell actually just collects some data here. And if you'd like to look at how the environment is structured, you can go over here. It's actually here in this environment.py. And you can see what actually what we are doing here, but it's at this point not so important. Let's just run this cell. And so what it's going to do here is obviously not only just import some libraries, but also import the agent and the environment, which come from these particular files. And we actually have a trained agent, and the model itself, the environment itself, is also running on has that surrogate model there. And so we need that file for that as well. And so we're going to run that. And the first thing we want to do is we want to see what happens when we just take random actions in the environment and what actually shows up. So how do we do that? And the way that we do that is that we perform actions by sampling randomly and giving a vector of length 3. And so the first value in this three-dimensional vector is this location, which is normalized. Oops, I should do this, which is normalized between 0 and 1 to apply the voltage itself. So you can choose a location along the wall. And so if it's 0.5, then it's going to apply it right in the middle. The second value is the magnitude of the bias or the amplitude. So again, it's between 0 and 1, it's normalized. And then the third value is, again, the magnitude of the pulse width, which, again, is going to be normalized between 0 and 1. And so in this case, what we are going to do here is that we are going to instantiate the environment. And so that's just using this particular line here. And then what we do is we effectively... oh, okay, yes. Yes, so here what we have done here is that we are taking instead of sampling a train policy, we're going to sample this random policy to get the action. So as I mentioned, the values are going to be between 0 and 1. Actually, to be honest, they're not between 0 and 1, they're between 0.1 and 0.9 for at least for the first positions case. That's just because we don't want to we don't want to deal with like the edge cases where we're too close to the edge and we don't have more information about what's happening around it. So, but anyway, we can sample from a random uniform distribution in this way, and then we can step the environment based on this particular action. We can see what reward we get, and then we can save the states, and then we can visualize what happens. So let's see what happens when we do this randomly. Has everyone got the Colab notebook to work? Are there any issues? Okay. So now let's print out what happens with the states. And so here, what's happening here is I am just printing out the states that we're getting. This is the final trial that we ran. So we ran 5 trials. I'm just going to look at the last trial and just see what happens, how the states evolve. And so this is what happens. This is what you can see the domain model looks like after all these biases have been randomly applied across here. It's kind of useful. You can have a look at more of them. Let's try again. It happens relatively fast. It's a fast kind of inference here. All right, so again, because it's all random, you're going to get different answers at every time, right? So what I want to do is I want you all to see if you can create a heat map, right, of the area under the domain model as a function of changing the bias amplitudes and pulse widths. So how would we do that? Well, basically, all you would have to do is you could fix this value here, like so you always apply at the same position, and then vary the values of the amplitude and pulse width in a systematic manner, save those states, and then see how the displaced wall, the area of that displaced wall changes as a function of these bias amplitude and pulse widths. So I'm going to give you a little bit of time to play with this. And so again, just repeating, this x-axis is sort of the domain wall itself, the 1D domain wall, and then on the y-axis you see the displacement of this wall from the original position. And so what we want to do is we want to see how the area of this changes as we change the bias amplitude and the pulse width. If you need to calculate the area, you can use the NumPy's trapezoidal integration to calculate areas. All right. So I hope you all had a chance to do that. So let's have a look at the solution that I came up with. Basically, we can step the bias values and pulse width values here. We can repeat this a number of times to get some statistics on the process or just get some better averaging. And we're going to look at an area around the domain wall that we actually want to focus on, right? So rather than integrating over the whole thing, we can just integrate around the region where we expect the change to happen. And so all I do here is I loop through the bias and pulse width values. I reset the environment. So we start from the flat wall configuration. And then I want to calculate what happens when I apply this voltage at the particular site. In this case, I'm going to choose exactly the halfway point. I'm going to step the environment based on this action. And this action is obviously always apply at that halfway point of that particular bias value, which comes from this array, and the pulse width value, which comes from this array. So once I do that, I can calculate my displaced wall. This is just looking at the area around where I applied the voltage, and then I calculate the area here. And so this area here is this trapezoidal integration that we can use to get an estimate of the area of the displaced wall. And then I run this and save the results in this heat map underscore results list. So if I make this an array first, let's see what this looks like. Let's see. Is again 64 by 3 because this is the bias. I save the bias, the pulse width, as well as the mean of the area. And so I can obviously plot this. So I want to plot the area, and it should be 8 by 8. Okay. And so what this looks like is kind of interesting. I don't know if this should be like this, but yeah. So this is as a function of the bias and the pulse width, how the area actually changes of the domain wall itself. Let's add some color bars just to see what that looks like. So there may be some issues with this. Maybe this particular area window is too small. I can make it a bit larger. But in general, this is how you would at least have a look at how the environment is behaving for different values of given actions, right? So typically in reinforcement learning, what you want to do is you want to start with an example of like what happens in a very particular, in a normal case where you just are applying actions where you already know what you're going to expect. And so by doing this, you get a handle for how good or bad, in a way, like how reproducible the environment actually is. What we can do though is we can also have a look at how the policies that we learned actually behave in this domain wall environment. So in this particular Colab, we also have the trained agents. So we trained the agents on a GPU server for a while. You can actually run it in Colab as well. That's in the next section. But for now, let's just run the trained agent and see what the trained agent actually provides. I'm just coming back here. So I don't know if this is flipped in some way or something, but it certainly shows that at least along one of the axes, as you increase the pulse width, it does seem like you have an increasing amount. Yeah, so you have an increasing amount of wall displacements. So there may also be a threshold at which you don't actually receive any, you don't actually move the wall. For example, for low voltages, it might be that even for large pulse widths, the wall doesn't move so much. There might be a threshold. So there might be that you expect, certainly you expect good values in this particular corner. Okay, so with this done, I think this one is done. Let's plot this and let's see what it gives. So again, this is showing a plot of what actions were taken by the agent. And so this looks quite similar to what I showed you in the presentation, but let's visualize what it actually looks like. here. And so here what you see is that this is the final wall. It didn't do so well here. It sort of overshot the mark here. But you can run this a few other times and see what that shows. It is a little bit stochastic. So you might have to run it a few times to get a better understanding of what's happening with the agent. So as you can see here, this is still requiring more training. It's still not perfect. And so if you want to actually train it yourself, you can actually use this code down here to be able to train the agent. And I'll walk you through that code. And so that's probably going to be the lecture today. But you can see that it's doing okay. It's obviously hasn't learned what to do on the right-hand side very well, but it has learned that you do try to maximize some rewards by applying more voltage pulses to the left-hand side. So that's something that's happening. All right. So I want to walk you through now an example of reinforcement learning training and how we would actually do that. So right now we have played with the environment, right? We just played with what happens when you change actions randomly and see what happens, or in a systematic way and see what happens to a particular state. Then I just showed you what happens when you run a trained agent. But I never went through the actual training itself and how that actually works. And so there's a bunch of parameters in reinforcement learning that need to be adjusted for different kinds of training settings and scenarios. One of the parameters, as I mentioned in the lecture, is the gamma, or the discount factor. So this gamma factor is 0.99 in this case, in which case we want a very long horizon for the agent, so that the agent can learn, from rewards that are well down into the future. We also have this function called generalized advantage estimation, which is another kind of layer on top of a discount factor, which I won't go into, but this is basically used for scenarios where you can sort of weight these gamma values as well, right? So it's another way of trying to reduce the variance that you get when you try to estimate these rewards. You can change the number of episodes per number of steps per episode. So in this case, we can change the number of times we can apply the voltage before we reset the episode. And then we can also train for different numbers of episodes. So typically you want to train for several hundred at least. I think in this case, we train for at least 5,000. It'll take a long time to train, but if you want to run this offline, you absolutely can. And there are two kinds of networks here. So we mentioned before the actor-critic algorithm. And so the actor-critic means that you have two different networks. One is the actor, which is the one that's creating the policy that you sample from. And then the other one is the critic, which is estimating the value of the states that you are actually in. Now, typically you want to adjust the learning rate for the critic to be a little bit higher than the learning rate for the actor, just so that you have a better baseline that you can subtract from. So the first thing to do here is that we instantiate the environment itself. So you can use any environment. Like if you want to use your own environments, you can call that here. You can use a bunch of different environments that are available in OpenAI Gym. The point is that you have an environment that you can call where you can then take actions, and then the environment will spit out states and rewards. So in this case, we are going to run through all the total episodes. So there are 5,000 here. And so we start with the environment being reset before we do anything. So that's normal. We start from a particular ground state, and then we run the state. So we have a particular policy, right? It's some kind of policy. It doesn't really matter. It can be initialized randomly in a neural network, and then we again sample this policy to get the actions, right? So as I mentioned before, we have three different actions to take, right? Like the action itself is a three-dimensional vector, and so therefore this is a multivariate, Gaussian distribution where I have these three different values for the mean and three different values for the variance to specify these three dimensions, and I sample from that, and that gives me my actions. So once I have these actions, I then step the environment. In other words, I provide the environment this action, and I perform the action on this environment. Then I save the states and rewards that I got. So I started from a state, I saved that. I chose an action, I saved that. And then I got the next state and I saved that. Okay. And so at the end of the episode, you have some kind of reward that is that full episode's reward. And we also just want to save that to see how we're performing. And then when we do this, once we have at the end of each particular episode, once we do this, we can stack these states, actions, and rewards together. We also have the done history. In other words, whether we ended up in a terminal state or not. And we put these together, and we can run it through a function which I wrote called the generalized advantage estimate, which is going to give us what is the advantage estimate as well as the value function, right? Based on the trajectories that we just saved. So it's going to return us that. And then once we have this advantage function and this value target, then we can then run our policy gradient algorithm, right? So what we can do is here we can find what was the probability that we took the log probability that we took these actions. So we have the policy. What was the log probability that we took these actions, right? And so that's just given by this particular line here. And then we just take the we take this particular log probability and multiply it by the advantage estimate, right? Which is exactly what was in the formula. And then we calculate the gradients that we then apply to the actor, and we apply those gradients to the actor. And similarly, we do the same thing for the critic, where we have the state values, in other words, what we expected to have from the state and what the critic actually predicted, what we got from the state and what the critic predicted what we would get from the state. And so we want to minimize that discrepancy using a mean squared error approach. And so this is still called the TD error, or temporal difference error. So we get a gradient from that, and then we then step the critic towards, try to minimize that particular loss function. So then we can then adjust the training, append these values to the training history. So we just so that we can visualize it later. So let's run this and see what happens. All right, so total episodes is not defined because I didn't run this. All right, so now what you will see is that you'll start to get some rewards. And so here's, the agent is training after every episode. It is updating its policy. Both the actor and the critic are being updated. And over time, hopefully you will see that there will be an improvement in the agent's performance. Now, there can be many reasons why it doesn't improve over time. One of the reasons could just be that you just don't have enough samples, and typically you need tens of thousands of samples before you will get good estimates of the gradient in reinforcement learning. But another thing could be that your particular neural network choice is not sufficient for the kind of problem that you are trying to solve, or maybe it's even too complicated for the kind of problem that you are trying to solve. So both of those can affect reinforcement learning training. There's also a bunch of hyperparameters here, and so you need to choose the right kind of hyperparameters for your particular problem, and it can be hard to know what that is without some trial and error approaches. There are other ways that we can use to try to get better reinforcement learning convergence. I won't discuss those here, but some of the ways include different kinds of algorithms. Things like soft actor critic is kind of the state of the art that's typically used right now. I mean, there are other methods as well, such as TD3 and so forth. But the point here is that there are newer algorithms rather than actor critic that can help to stabilize the training more than what we get here. And similarly, if you have environments which are not particularly, which are not representative of your actual environment. In other words, if the surrogate model that we create is not the same, providing the same kind of results as what we got in the actual microscope, then that can also be an additional source of error that can prevent you from learning good policies that you end up deploying. So these are things to keep in mind when you actually use reinforcement learning. And you can see that it's very noisy initially, right? So you might get quite a few hundred episodes where it even seems to go negative. It even seems to go in reverse. But over time, you should see that when you plot it, you will eventually get some improved results. So for example, here we got one where the reward is -7 and not -9. So it suggests that at least in that case, it found some decent set of actions. Another way that we can improve this is we can learn, instead of a single policy, we can learn distributions over policies. And we can leverage variational methods to be able to find the gradients there, and high performance computing resources to be able to collect more transitions to be able to estimate those gradients. So those are all sort of advanced computational topics, but these are the kinds of things that are required in order for us to be able to deploy reinforcement learning in microscope operations. It's still a very challenging problem. However, it is also a very satisfying way to be able to create automated agents, I think, right? Because you can really solve very challenging problems that are otherwise, that we don't really know how to solve in other ways, and right now are very challenging to automate. at least this provides us a strategy that we can use to be able to do that. And I think it can be highly helpful in the materials design and optimization space as we get better at applying reinforcement learning for these problems. Are there any questions? The quiet crowd. Okay. Getting them
getting them started early.
started early.
So
Yeah.
that they can be a voice of approval.
Nice. It's never too early for reinforcement learning. How can physics be incorporated into the reward functions? This is a really great question. This is, well, one of the things about reward function crafting itself is a very challenging endeavor. And the reason is because typically your reward function, if you craft it in an incorrect way, the agent will find a hack to be able to maximize a reward that is not necessarily what you want, right? So, for example, if we go back to the dopant manipulation system, if you craft a reward function where you only put the final state of of the system as your reward, where you just want these dopants to be agglomerated towards the center, then it turns out that the way that it can do that is to blast away all the atoms and not care about the rest of the lattice when you end up moving the dopants towards the center. And this is obviously not particularly good, because it means that you don't have a lattice so much to be able to play with anymore, and to be able to see those effects of those dopants in that lattice. So you actually absolutely need to be able to provide the correct kind of regularizations to avoid scenarios that you didn't actually want by crafting your reward function itself. Now, as far as incorporating physics is concerned, that's an interesting one. I haven't fully thought about it. And typically, we incorporate the physics into the surrogate model that we learn. However, there are sort of ways that even in model-free cases where potentially you could incorporate some level of physics into the training process, but I don't think you would do that in the reward function in most cases. However, that's an interesting problem. I haven't fully thought about the reward functions in terms of applying physics constraints to them, because usually it's what you want from the end solution, right? So whatever state you want at the end, or whatever property you want to be maximized, is what the reward function will be. And the physics constraints come in terms of the agent's policies themselves or in the underlying surrogate model. Are there other questions? So you're all reinforcement learning experts now. It's an interesting, it's a good field to get into, and I think it's one where there's a lot of promise for the future. It does require good access to, you have a collab, you have access to compute resources, and it requires, some simulations or an ability to at least perform experiments rapidly. And both of those things are things that you've heard about in this school, where we talked about how we can potentially generate data through different kinds of models, as well as potentially increase the speed at which we can acquire data through machine learning approaches on microscopes. So those are the things that are sort of fundamentally required to enable reinforcement learning, but also incorporating the physics constraints allows us to be able to do better with the minimal amounts of data that we actually have. So if we didn't train our environment with a good amount of physics regularization, it would do much worse than actually what we're doing. So all right. If there are no more questions, I guess this should wrap up the lecture.
Thank you, Rama.
Okay. Well, thank you all for coming.
And cut.